In this section, we will examine various proposals for achieving mutual exclusion, so that while one process is busy updating shared memory in its critical region, no other process will enter its critical region and cause trouble. The first one is disabling interrupts. On a single processor system, the simplest solution is to have each process disable all interrupts just after entering its critical region and re-enable them just before leaving it. With interrupts disabled, no clock interrupts can occur. The CPU is only switched from process to process as a result of clock or other interrupts, after all, and with interrupts turned off, the CPU will not be switched to another process. Thus, once a process has disabled interrupts, it can examine and update the shared memory without fear that any other process will intervene. This approach is generally unattractive because it is unwise to give user processes the power to turn off interrupts. What if one of them did it and never turned them on again? That could be the end of the system. Furthermore, if the system is a multiprocessor with two or more CPUs, disabling interrupts affects only the CPU that executed the disable instruction. The other ones will continue running and can access the shared memory. On the other hand, it is frequently convenient for the kernel itself to disable interrupts for a few instructions while it is updating variables or especially lists. If an interrupt occurs while the list of ready processes, for example, is in an inconsistent state, race conditions could occur. The conclusion is, disabling interrupts is often a useful technique within the operating system itself, but is not appropriate as a general mutual exclusion mechanism for user processes. The possibility of achieving mutual exclusion by disabling interrupts even within the kernel is becoming less every day due to the increasing number of multi-core chips even in low-end PCs. Two cores are already common, four are present in many machines, and 8, 16, or 32 are not far behind. In a multi-core, that is, multiprocessor system, disabling the interrupts of one CPU does not prevent other CPUs from interfering with operations the first CPU is performing. Consequently, more sophisticated schemes are needed. The next proposal is lock variables. As a second attempt, let us look for a software solution. Consider having a single shared lock variable, initially 0. When a process wants to enter its critical region, it first tests the lock. If the lock is 0, the process sets it to 1 and enters the critical region. If the lock is already 1, the process just waits until it becomes 0. Thus, a 0 means that no process is in its critical region, and a 1 means that some process is in its critical region. Unfortunately, this idea contains exactly the same fatal flaw that we saw in the spooler directory, the one discussed in critical regions PowerPoint presentation. Suppose that one process reads the lock and sees that it is 0. Before it can set the lock to 1, another process is scheduled, runs, and sets the lock to 1. When the first process runs again, it will also set the lock to 1, and two processes will be in their critical regions at the same time. Now you might think that we could get around this problem by first reading out the lock value, then checking it again just before storing into it. But that really does not help. The race now occurs if the second process modifies the lock just after the first process has finished its second check. The next proposal is strict alternation. A third approach to the mutual exclusion problem is alternation, and it is shown in this code. Code snippet. This code snippet or program fragment, like nearly all the others in the Modern Operating Systems book by Tannenbaum and Boss, is written in C. C was chosen here because real operating systems are virtually always written in C, or occasionally C++, but hardly ever in languages like Java, Python, or Haskell. C is powerful, efficient, and predictable, characteristics critical for writing operating systems. Java, for example, is not predictable because it might run out of storage at a critical moment and need to invoke the garbage collector to reclaim memory at the most inopportune time. This cannot happen in C because there is no garbage collection in C. A quantitative comparison of C, C++, Java, and four other languages is given by Fredschelt, 2000. Okay, as you can see in this program fragment, the integer variable turn, initially 0, keeps track of whose turn it is to enter the critical region and examine or update the shared memory. Initially, process 0 inspects turn, finds it to be 0, and enters its critical region. Process 1 also finds it to be 0, therefore sits in a tight loop continually testing turn to see when it becomes 1. Continuously testing a variable until some value appears is called busy waiting. It should usually be avoided since it wastes CPU time. Only when there is a reasonable expectation that the wait will be short is busy waiting used. A lock that uses busy waiting is called spin lock. When process 0 leaves the critical region, it sets turn to 1. To allow process 1 to enter its critical region, suppose that process 1 finishes its critical region quickly so that both processes are in their non-critical regions with turn set to 0. Now process 0 executes its whole loop quickly, exiting its critical region and setting turn to 1. At this point, turn is 1, and both are executing in their non-critical regions. Suddenly, process 0 finishes its non-critical region and goes back to the top of its loop. Unfortunately, it is not permitted to enter its critical region now because turn is 1, and process 1 is busy with its non-critical region. It hangs in its while loop until process 1 sets turn to 0. Put differently, taking turns is not a good idea when one of the processes is much slower than the other. This situation violates condition 3 set out in the critical regions PowerPoint presentation. Process 0 is being blocked by a process not in its critical region. Going back to the spooler directory discussed previously, if we now associate the critical region with reading and writing the spooler directory, process 0 would not be allowed to print another file because process 1 was doing something else. In fact, this solution requires that the two processes strictly alternate in entering their critical regions. For example, in spooling files, neither one would be permitted to spool two in a row. While this algorithm does avoid all races, it is not really a serious candidate as a solution because it violates condition 3. Next, Peterson's solution. By combining the idea of taking turns with the idea of lock variables and warning variables, a Dutch mathematician, T. Dekker, was the first one to devise a software solution to the mutual exclusion problem that does not require strict alternation. For a discussion of Dekker's algorithm, see Dijkstra, 1965. In 1981, G. L. Peterson discovered a much simpler way to achieve mutual exclusion, thus rendering Dekker's solution obsolete. Peterson's algorithm is shown here. This algorithm consists of two procedures written in ANSI C, which means that function prototypes should be supplied for all the functions defined and used. However, to save space, we will not do prototypes here or later. Before using the shared variables, that is, before entering its critical region, each process calls enter region with its own process number, 0 or 1 as parameter. This call will cause it to wait, if need be, until it is safe to enter. After it has finished with the shared variables, the process calls leave region to indicate that it is done and to allow the other process to enter, if it so desires. Let us see how the solution works. Initially, neither process is in its critical region. The process 0 calls enter region. It indicates its interest by setting its array element and set turn to 0. Since process 1 is not interested, enter region returns immediately. If process 1 now makes the call to enter region, it will hang there until interested 0 goes to false. An event that happens only when process 0 calls leave region to exit the critical region. Now consider the case that both processes call enter region almost simultaneously. Both will store their process number in turn. Whichever store is done last is the one that counts. The first one is overwritten and lost. Suppose that process 1 stores last, so turn is 1. When both processes come to the while statement here, process 0 executes it 0 times and enters its critical region. Process 1 loops and does not enter its critical region until process 0 exits its critical region. The code is shown in the next slide here. As what you can see, it is essentially the same as the solution with TSL. All Intel x86 CPUs use exchange or XCHG instruction for low-level synchronization.